sine of pi on 2 minus x times cotan pi on 2 plus x equals minus sine of x. So all that simplifies to something pretty simple, right, Joanna? So I would think that we would start with the left-hand side, correct? There's kind of no doubt there. So I've got sine of pi on 2 minus x times cotan pi on 2 plus x. Okay, so that's my left-hand side. Now, what occurs to you when you first look at this identity? What are you thinking? Anyone?
Sine.
Yeah, the sum and difference identities, right? So this is the sign difference identity. So when I look at this like the sign difference identity, this one, this would be my angle A, right? This is what I would represent as angle A, angle B, and this would be my A and this would be my B for this identity. But let's just take a look at the sign identity. So if I list it out, it would give me sine of A times cos of B subtract cos of A times sine of B. Okay, so that is multiplied by, I'm going to have to run over into my right-hand column, by cotan of pi on 2 plus x. Now, I don't have a formula for cotan. I have a formula for tan. But remember, we can look at cotan as in two different ways. Cotan is equal to 1 over tan, right? Cotan equals 1 over tan. But cotan also equals cos over sine, right? And I think I'm going to choose the cos over sine one, even though it's going to be longer. But remember our kind of rule, like when we're faced with something super tough, one of the methods is, the strategies is put everything in terms of sines and coses. Agreed? Yeah. Also, I know I have to do tons of canceling. Tons of canceling have to be involved in order for this all to just cancel it to minus sine. Agreed? Once again? So I'm going to do the cos over sine. So I'm going to multiply this by, whoops. I am going to, this is my little thought bubble. I'm just going to move up here for a sec. My cotan, I'm going to think of it as cos of pi over 2 plus x all over sine of pi over 2 plus x. Okay, that's how I'm defining this cotan. I go back to my sum sheets. Now cos, the sum of cos A plus B is equal to cos of A times cos of B minus sine of A times sine of B. So that's my numerator, and my denominator is the sine addition. So this was sine difference, now I'm doing sine addition. Sine addition is sine of pi on 2 cos of B plus cos pi on 2 times sine of B. Okay? Now, the nice thing about this is, even though, again, in identities, as I've said many times, sometimes, gentlemen, could you close the door, please? Sometimes things get worse before they get better. But when they get worse, when I have lots of pieces going on, I can usually do some canceling, right? So the nice thing too is they gave us one real value and one variable. The real values, lots of times they'll have zeros and ones and they end up canceling. Okay, so what do we have here? Sine of pi on 2 is just 1, agreed? So I'll have 1 times cos of x minus, what's cos of pi on 2? 0 times sine x. So this whole thing is just going to be reduced to cos. So I'm just going to leave that for now just to show you how I got all my values. And once again, cos of pi on 2 is 0 times cos of x minus 1 times sine of x all over 1 times cos of x plus 0 times sine of x. Now, when you're doing your work on your own, as soon as you get 0, you might not even want to bother writing that down. But I'm writing you down so I can clearly show you how I got all my values. All right, so this just disappears, right? And I'm left with just cos of x here. And it's being multiplied by, okay, what do I have here? What am I left with here? Okay, that disappears. This one disappears and this one disappears. So I'm left with negative sine x over cos of x. And what happens? The coses of x, and I get my minus sine x, left-hand side equals right-hand side. So that's just one where you just have to keep powering through, right? And because they gave you pi on 2 as a value, you know that the coefficients of pi on 2 for sine and cos are zeros and ones. That really simplifies things a lot. Okay, you said also number 6, Joanna? Or, yeah, number 6? Okay. So let's do number 6. Now this was a really tough one. It wasn't so tough in the end, but I think it was tough to start. How many people tried this one? John, were you the only one? What was your system? What did you do? Put everything into sines and coses? Okay, let's try that then. This is I'm going to say one thing. I found this one tricky too, because isn't this the one that John and you and I were talking about, and it simplified to something really simple? Okay, so did you do that too? Did you simplify one side and it just kind of all became tan? Is that what happened? Okay, you did sines and coses. How did you approach this one, Joanna? Did you do sines and coses, or did you leave everything in tans? Sine and cos? Okay, so let's try that way because that's what they did. Carl, did you try this one? No. Okay, anyone else try this one? Adam, did you? No? And D, did you get this far? Number 6? No. Okay, so let's try sines and coses. We'll catch up to John and Joanna. Then I would think of this. I'll start left-hand side, I guess. It probably doesn't really matter. Let me start left side. Okay, then what did you do? Did you combine fractions? Okay, so I'm not going to bother writing every step out. LCD, the LCD would be cos, right? So on my top I would get what? Cos plus sine all over cos divided by sine plus cos all over sine. Joanna agrees, John, you too? Okay, so then when I do I've got stacked fractions, lots of times things cancel, and sure enough that happens this time, right? I'd have cos plus sine over cos. I'll show this step. This would become multiplied by the flip. So I'll have sine over sine plus cos. So these two these two cancel, perfect. So I'm left with sine over cos, which I know you got that, John, right? So at this point, it would take a lot of work. This is one thing to keep in mind, everyone, even if you haven't tried this one yet, because you might get something similar. If you get something that simplifies so beautifully and so succinctly and so efficiently to one term, I mean, I could call this tan. I'll leave it as sine over cos. Leave it, because this one looks very similar, right? It would take me a lot of mathematical manipulations to convert this to this, and I'm not even sure how to go about that. But if we do the same thing with this one, let's see if we can reduce that to sine over cos, because if you can reduce that to sine over cos, you've proved left-hand side equals right-hand side. Okay, so take a minute and see if you can convert this one to the same thing. Then that's another way to prove an identity. You don't always have to take it all the way. This is an example of working both sides independently. And if you work both sides independently and they arrive at the same thing, you've still done the same job. So keep that one in your back pocket. Think about, like, if you do all some really good stuff and it ends up being something really simple at the end, it would be really hard, like, to convert it back. So then just see if you can work the other side the same way. Did you get it? Yeah. Because it's pretty much the same one, except all the signs are just flipped, right, in a way. Okay, so equals. So then we get cos minus sine over cos, all divided by oops. Okay, so again, these cancel, and I'm left with sine over cos. So your job is to prove left-hand side equals right-hand side any way you want, right? So left-hand side equals right-hand side. What about, anything else? We did number 2 and 6 on the problem section. Anything else? The problem section? Okay, let's try that one. Number 4. So number 4 was this one, John? Okay, so let's take a look at number 4. Okay, what side did you start with, John? Left? Yeah. Did you try this one, Neville, at all? Did you get this far? What was your strategy, Joanna? Did you factor? You factored both? I think I could factor both of these, right? Remember the F word? I said to you, remember the F word? I think factoring is the most important F word in identities. The next most important would be fractions, right? To think of fractions. But here, I'm going to think of factor. And how does the top factor? Difference of squares, right? So I have cos minus sine times cos plus sine. Now, the bottom factor is 2, right, Joanna? Because they have a GCF, right? GCF of cos. So pull that out. So I'm left with cos plus sine. Okay, so I can do some heavy-duty canceling. These guys cancel. So now I'm left with cos minus sine all over cos. Now, one thing to remember is, you know how sometimes you have two parts? Like you might have an identity with, I don't know, it might look like this. I've said to you guys before, you might have like a sign over cos minus 1 over, I don't know, I'm just making things up here. And this side is like tan times secant, we'll say. I'm making this up. I don't think this is an identity. So one of the strategies I tell you, your second F word is fractions, right? If I start with two pieces and my goal has only one piece, I use fractions, LCDs, to push them together to 1, right? This is an example of the reverse. I have one piece and I want to move it apart to two pieces, right? This is regarded as one piece because it's sitting over one denominator, and my goal is two separate pieces. So as long as I have one denominator, I can split these two terms into separate fractions, right? They merged together because they had an LCD. Now I want to separate them. So they will become cos over cos minus sine over cos, which is perfect. Now I have my two pieces separated with a minus sign. Cos over cos is 1, and sine over cos is tan. So our fraction trick, when we use fractions to push things together, can be also used in reverse. We can use, as long as they have the same denominator, you can split them into separate pieces, right? Yeah. Okay, anything else up here on this that I did post the answers to, and don't get really hung up on the answers to the identity section, the problems, because the identities can be approached many different ways. So if you did a different way, as long as you got your goal, your other side, then that's fine. I mean, if you get super stuck, you can look at how the answer key did the identities, but there's not only one way to approach an identity. Okay.
How about number 3?
Which one?
Number
3. On the same section?
Yeah.
Did you try this one, Rahel? Yeah? Okay. I think this is an example of one of those ones that gets really big before it. Okay, so I'm looking for help here. How did anyone approach number 3? Well, a couple things I see. I have double angles here and only single angles here, right? So somehow, and I think I'm going to start left. There's not much to work with here. So I have to use the double angle formulas will convert double angles into single angles, right? So let's see. My only problem is this cos of 2 theta, right? So what am I going to do here with my cos of 2 theta? Use the double angle formulas, right? This requires a lot of thinking. Now you can always, it might take you longer, but you know what I see here? Remember that we've got 3 forms for cos 2 theta. These ones have to disappear somehow, right? Because they're not over here. So how would I get rid of this 1 using the double angle formulas? I've got 2 versions with a 1 in it, right? I think this second one, right? That will get rid of the 1. So that's, I think, what I'm going to do, because that would at least give me a place to start with. So what I'm doing is I'm just replacing this cos 2 theta with, okay, I'll show you what I'm replacing it with. 2 cos squared minus 1. right? That's what all I did was just replace that one. Plus, the nice thing about sine 2 theta is there was only one way to get rid of the double angle, and it's 2 sine theta cos theta. Okay, all over. Now, this one's a little bit different, right? To get rid of this one, I think I'm going to have to use the other option, right? Or no, I think I still can use the same one, right? 1 plus, okay, what has to go in here to get rid of the 1? It has to be a negative 1 again, so it should be the same one, agreed? Right? Because a negative and a positive, and this is a positive and a negative. Okay, so now let's see what I have left here. I have the 1s are going to cancel out, right? No, I did that wrong. Sorry, this is the wrong one, right? Sorry, wrong. This has to be 1 minus 2 sine squared theta. Sorry. Otherwise, the 1s don't cancel, right? 1 minus 1. Okay, that's gone. And then a positive, or a negative and a negative make a positive. So my top is going to be 2 sine squared theta plus 2 sine theta cos theta. That's kind of nice, right? I see a lot of common factors there. The 1s cancel, and I'm left with 2 cos squared theta plus 2 sine theta cos theta.
Is there a minus over the 2 sine squared theta?
Did I copy the question down wrong? Minus plus plus plus. I replace this with 1 minus 2, right? 2 negatives make a positive, right? Okay. So what do I have in common here? Now I have GCFs, don't I? I have GCF on the top of a 2 sine theta, right? And that leaves me with sine theta plus cos theta. I'm hoping something similar happens downstairs, right? Down here I have a 2 cos theta as an LCD. That leaves me with cos theta plus sine theta. And these two are the same, right? Or the additive properties are it doesn't matter if I add sine and cos or cos and sine, they're the same. Okay, so my 2's cancel as well, and I'm left with 10. Now the hard part was this, right? But if you make an error, you can just do what I did, right? There are 3 versions of cos, so you got to use the one that works best for you, right? In the situation and what your goal is. Okay, I'll leave that now because I could sit here and do this all day, but I'm not going to. Work a little more on your own. Of course, if you have questions, go consult the blog and you can look at how they did the questions, or you can come and see me. That's always an option, right? But I'll let you work on that a little bit on your own now. Make sure you get through most of this, or you look through it before your test, which will be next week. And I think I'm looking at Friday of next week for the next test, to be honest. All right, so what do we have now? We've got 2 topics left in trig, and it's been a long haul for trig, right? But the last section we've been doing is just the equations and identities. So I wanted to cover all the identities before we talked about equations, because sometimes you need an identity to solve an equation. So that was why I kind of put the stall on and we'll learn the identities, and now we're going to go back to equation solving. And the reason I say go back to equation solving is because we've actually solved trig equations already, little ones. And I remember telling you that before. Anytime you were asked to solve for an angle, when you were identifying the 6 trig ratios or the 5 trig ratios, and then you were asked to solve for the angle, that was a trig equation. Anytime you're solving for angles, it's a trig equation. So I just want to let you know what they've got printed for here, and then we're going to do some examples in the pink booklet. But it says, I like how they printed it here. We have already solved some trig equations degree 1, like very small baby equations in a previous section, but we didn't treat them as equations. Like I really didn't use the word equation a lot. I just kept saying find the angle, find the angle. And that's how we tend to introduce the trig equations. So it says, an example is solve sine theta equals a half over the domain 0 to 2 pi. This is actually a trig equation, right? A big trig equation. So we've already solved them. What we're going to do is just explore some tougher, more complex equations rather than just the very small first degree, and we also work our way up to second degree equations, and those are the squared quadratic trig equations. But you use all the skills you used before in your previous sections for solving equations. They talk about solving equations graphically or algebraically. We could solve a trig equation graphically, but we're not going to do that in this section. You've already learned how to graph trig equations. You could certainly solve a trig equation graphically. That means you're going to graph it and look for the x-intercepts, right, where it crosses the x-axis. If you did that, you would graph the trig function. You would substitute 0 in for y and solve for x, which is essentially what we're doing algebraically, right? So there's no difference really for us solving graphically and algebraically. In pre-cal, they end up being the same thing because you're finding the x-intercepts. I think in some provinces they allow you to use the graphing calculator, so that's what they mean by solving graphically. You would punch the equation in the graphing calculator, find the x-intercepts, and then state them that way. That's not an option for us in Manitoba. So we're not going to solve equations graphically. You just have to know how to produce a trig graph, but we're not going to actually use it for solving trig equations, okay? So again, I'll write this down on the blog of the pages that you could look over, and they've got lots of examples here for you. I am going to go over similar examples. So once again, we're not going to solve them graphically. So they've got solving equations. These are the techniques we're going to use. We're going to use factoring again. Sometimes if you can't factor a trig equation and it's a quadratic, guess what? You can use the quadratic formula. So don't forget, any technique you learned in previous sections, you can use in trig because it's just solving an equation, right? So all the skills you've learned before can be brought over to this section. Again, we're going to do the graphing approach. So we end up doing, again, you can see we end up doing some quadratic trigs. And then page 213, I'm not going to talk to you about today. It's solving for multiple angles, so sometimes we'll have a double angle. Tomorrow I'll talk a bit more about that. But your homework will end up being on part of 6.4. But let's take a look first, get our head back into solving equations with trigonometry. And once again, all this double angle stuff, it's going to come probably tomorrow. I told you guys to, we're just going to put a pin in that. So I'm on page 16. And it says solving first and second degree trig equations. First degree just means normal ones. Second degree means quadratic, right? Power 2. So we'll start with a couple of these, and then we'll, I have to make sure there's a quadratic in here. I think I might have missed that one. Okay, example 1. Solve the equation cos theta equals -1/2 over the domain 0 to 360. All right, you've seen that before, right? Anytime you can solve an equation using exact values, we should do that without a calculator. This is one of our exact values, right? So we're going to do this, no calculator. Where does cos have a value of 1/2? Right, so my reference angle is 60 degrees, okay? Now, it says just one quadrant. So where is cos negative? 2 and 3. So what are your 60-degree angles in quadrant 2 and 3? 120 and 240. That's it. Okay, you solved a trig equation. In the end, even when you have the complex one, the very last step of any trig equation ends up just simple, like this is the step that you're going to do in your very last step of any trig equation, even a quadratic one. Okay? So once it says, when we're solving a first degree trig equation, isolate the trig function. So the trig function's all by itself, and then you're ready to, it's in this form, right? So we do everything we can to get it in this form with the trig function isolated. So let's try this one. Solve the equation root 2 sine x minus 3 equals negative 2, 0 to 360. Okay, that looks a little more difficult at the start, right? So what we're saying is we want to get it into this form with the trig equation isolated. So the trig equation, the trig function is the sine x, right? I want to get sine x isolated. Notice we can use a theta or an x. If there's a variable of any kind after the sine, cos, or tan, that's the variable you're solving for, and that's representing the angle. So what's the first thing we would do here? Transfer the 3 over, okay? So that gives me root 2 sine x equals 1. Agreed? Okay. And now I think everyone would agree we're going to divide through by the root 2. So I have sine of x equals 1 over root 2. Now this is where it becomes very important that you can recognize rationalized or unrationalized. Does anyone recognize 1 over root 2? That's the same as root 2 on 2, right? So where does sine have a value of root 2 on 2? What's my reference angle? 45. Now, I'm going to approach the same way as I always do. I write my reference angle down. I identify where sine is. Okay, when I had it isolated at this step, or this step, sine is positive, right? So that would be quadrant 1 or 2. So theta will equal 45 degrees, or 135. So that's not so hard, right? You've actually done you've actually solved many times at this step. You just have to put it in this step. You just have to use all your algebra skills to isolate the trig ratio. And then you're good to go. Okay? What about the next one? Now, notice this is the actual equation. It's kind of hard to see, but the actual equation is 5 tan theta plus root 3 equals 2 tan theta. Okay, you've got tan thetas on both sides. So what do your algebra skills tell you to do? Put like terms together. Should we push all our like terms, our tans, to the left? So let's try that. So I have 5 tan theta minus 2 tan theta. Now this doesn't have any tans, so I'm going to push him over to the other side. Negative root 3. Because I'm trying to isolate tan. The only way I put all my trig stuff on one side, my constants on the other. Okay, what do you think 5 tan theta minus 2 tan theta equals? 3 tan theta. Okay, last step. There, so tan's isolated now, right, D? Okay, so what's my reference angle for root 3 on 3? Like I don't think of the negative when I'm doing my reference angle. It's where is tan equal to root 3 on 3? Radians. So it's pi on 6. Okay. Now, this is tricky. They gave me a negative revolution. This can be the hardest part, right? Looking at the revolution is negative. All right, so I first have to identify the quadrants where tan is negative, right? So I'm going to do that as well. So that's my little tan theta is negative in quadrants, what, 2 and 4? So that's where I'm looking. This is quite tricky. Now, instead of going in the positive direction, they're making me go in the negative direction. So I have to stop here. So this would be, sorry. If you want to think in degrees, I suppose you could think in degrees and then convert back, right? Or let's just think about this because it's a negative revolution. Think of it in 30 degrees and then we'll convert back. Okay, so here's quadrant 2 and 4. Here's my first angle. So what would this measure be? Negative 30 degrees, right? Or negative pi on 6. Okay, let's go all the way around. And now it's 30 degrees, or pi on 6 past here. So it would be what, negative 210, or negative, well this is 6 sixths, so 1 more sixths, negative 7 sixths. So my answers are pi equals negative pi on 6, negative 7 pi on 6. The trickiest thing I think is to look at the domain, right? Because it could be a different domain. Are we okay with that? I think everyone's probably fine up to here, right? I think everyone's fine with isolating. The hard part comes, okay, now I have to remember my unit circle again. If they give me exact values, you have to remember your unit circle, and you have to pay attention to what the domain is, right? As well as is it in degrees or radians. All right, so now those were exact values. It's not always going to say to you solve exact values, although you'll know for sure when you get your exam because you only have your calculator for a small part of it, right? And then you have to give it up. So you'll know that most of your exam questions are going to be exact values. Now this is approximate. Anytime you see the word approximate or rounding, it'll tell you to round to 3 decimals, so I'll also add that in. Round to 3 decimal digits. You know you're allowed to use your calculator. You also know probably they aren't going to work out to the exact, they won't be nice values, right? They'll be values that aren't a part of our special set of angles. So that's another hint for you to use your calculator. So you definitely need your calculator today. So everyone can pull their calculator out. Pay attention to if you should be in degree or radian mode. Solve the equation. 5 secant x minus 4 equals 8 from 0 to 360. Okay, I'm going to let you set things up first. Set this equation up. So it probably shouldn't take you that long. What did we get? We got 5 secant x equals out of 4, 12. So then I get secant x equals 12 fifths. All right. If I had a secant button on my calculator, I'm good to go, right? I just pick my calculator up, go shift secant, but I don't. So what could I do here? Yeah, I could just flip over, the ratio, the value itself flips, so that means cos equals to 5/12. Okay, now should be in degree mode because they told me solve in degrees. Let's do for degrees, let's do 3 decimal digits again. Let's push our skill level. Okay, first thing I do, whether it's positive or negative, I solve for my reference angle, right? If this was a negative sign, I wouldn't punch it in. Okay, so I get this, 65.376 degrees. Agree? Okay, so this could be one of my answers because I'm solving for one positive rotation. Cos is a positive value, so it's quadrant 1 or 4. So I got lucky. My first answer is 65.376 degrees. Now, I think I'm going to leave this in my calculator. I know it's 360. Take away this, right? So I'm going to just go my negative 360, and it's going to be a positive then, 294.624. And those are my two answers. So not much new to learn yet. There's a couple of new things. Just I think the quadratics will be maybe a little different, and the multiple angles, which I'm going to leave till tomorrow. But try the next one on your own. Try that next example on your own. Then I'll do, we'll finish example 4 and I'll let you guys go for break. Then we'll tackle some quadratics after break, and then that'll be it for today. Then I'll give you some work time. We're just solving trig equations at Part 1, which we've kind of done before already, right? Remember when you had to find the 5 trig ratios and then find the angle associated with them? That's what we did. They're just going to get a little more complicated. What's happening? Okay, so what did we get here? I think I would have moved the tan to the right. I guess it doesn't really matter. How many people moved tan to the left, kept tan on the left? How many moved him to the right? To the right? Right? How many people to the right? A few more? Okay, so Neville, you lost out this time. Okay? So 5 take away 9 will be negative 4. It all works out to the same anyway, right? If I moved them to the right, I keep my tans positive, but my constant's negative. So it's kind of 6 of one, half dozen of the other, right? So then I have what? Negative 4/5 equals tan. Right? All right, so tan is negative. I'll just keep this in mind. Tan's negative in 2 and 4. Solving in radians, so I had my calculator on degree mode. I'm going to have to flip to degrees, or so to radians from degrees. Okay, so make sure you pay attention, right? It's going to flip-flop on you all the time. Now, I don't punch for my reference angle. Remember, for reference angles, you don't punch in any negatives. You're just going to do this. You're just finding your reference angle. You've already used the negative to identify your quadrants. Your negative only helps you identify your quadrants. Now, this isn't my special values, right? So I got to use my calculator. So shift 10, 4 divide 5, and I get a reference angle of 0.6747 dot 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 dot, right? So I'm going to store mine. And again, it'd be really helpful if you could figure out how to store your reference value or reference angles. So now I'm going to do, it's going to be pi, subtract my reference angle, and then 2 pi, subtract my reference angle, right? Okay. So pi, subtract my stored reference angle, and I get theta equals 2.467 to 3 decimals, or 2 pi subtract my stored angle, and I get 5.608. Okay, so those are my 2 answers. Ooh. How many people were successful? Excellent. Okay, let's take a look at this last one because it's not much new, and then I'll give you guys a break and we'll look at the quadratics, what a quadratic trig looks like. It sounds really fancy and complex, and it's really not. It's very simple. Okay, there are, we know this already, right? There are infinite solutions for any trig equation, unlike an algebraic equation. Because if I gave you like just a baby trig equation, let's say I just told you to solve this. Solve sine theta equals, let's just do this one, a half. And I'll let you solve in degrees. Solve in degrees. But I don't give you a search area. I don't give you like a domain. I don't say from 0 to 360. What do you have to tell me then? Where does sine equal a half? 30 degrees, or sine's positive here and here. 150. Okay? So those are my answers, right? But if I don't tell you just one revolution, you have to say, oh, I can go infinite times, right? Every time I travel, if this is where 30 degrees is, every time I travel around, I'm going to hit that 30. Sine's going to have a value of a half again. Same on this side. So I have to say what? We did this before. 360 times k. 360 times k. K is any integer, right? Remember we did that? So if you're not given a domain, if you're not told start and stop, then you have to include the general solution. The other words you got to look out for, it might just tell you write the general solution. They're just getting you to solve for all angles, right? This means your answer should be all angles possible from this. Your domain isn't 0 to 360 anymore, or 0 to 2 pi. It's like negative infinity to positive infinity. That's your domain, okay? So they kind of did a two-part here. It says solve the equation cotan plus root 304. So do it for 0 to 2 pi. Then write the general solution. Those words, general solution, just means solve to infinity. Okay? And sometimes they'll just slip, they'll just say, you won't usually have both. It'll say, find the general solution for this. All right, so cotan, let's see what we got here. Cotan equals negative root 3. Now this is one of my special angles, so I could either think of it as cotan equals negative root 3, or I could think of it as tan equals negative 1 over root 3. When does that happen? What's my reference angle for the tan equal 1 over root 3? Or I guess that would be 1 over root 3 or root 3 on 3? Pi by 6, right? That's my reference angle. Okay, so this time though, tan is negative, tan and cotan are negative, so again, we've seen that again and again in quadrant 2 and 4. So what are my answers? What are my pi on 6s in quadrant 2 and quadrant 4? Right here. What's my quadrant 2 pi on 6? 5 pi on 6? And what's my quadrant 4 pi by 6? 11/6, yeah. Okay, so that's my solution from 0 to 2 pi. Now, if they want the general solution though, I just add in my plus 1 revolution times k. Now I can't use 360, so I have to use 2 pi k. This is just stating all the coterminals, right? There. So that's kind of nice because you've seen that before. That's not brand new. I think the brand new thing is the word general solution, or the term general solution. That means solve to infinity. Okay. One last one, and then you guys go for break. Solve 7 sine theta minus 2 equals 4 sine theta minus 1. Okay, so a couple things with this one. Got sine theta as a third, right? Is that one of my special spots? No, so I'm gonna have to use my calculator. This time you weren't given any instructions, so write the general solution, but you weren't told radians or degrees, so I guess it's your choice. So what do you want to solve for? Degrees or radians? Degrees, I think. Oh, you go degrees if you got the choice, right? So we'll solve in degrees. Clear. I'm going to have to change my mode. Okay, so I'm solving in degrees. Let's, as a nice little present to ourselves, let's say round to the nearest degree. Make it even nicer. No decimals. Okay, solve in degrees to closest degree. General solution. Okay, so my reference angle is going to be what'd you get for reference angle? 19. Perfect. Okay, sine is positive, so that's going to be quadrant 1 and 2. So my first answer is just 19. Got lucky there as well. And then second angle, 161, perfect. There's my solution for one revolution, but if they want all revolutions, I just have to add all my coterminals. And there we go. So lots of old stuff here, a little bit of new stuff, but mostly old stuff, so that's great. Let's take a break, and then we'll just talk. I'm going to skip over, like I'm